Hi, welcome to this Corbettmaths video. In this video, we're going to look at the video solutions to the error intervals practice questions. If you need any extra help on error intervals, if you go to corbettmaths.com/contents and scroll down to video number 377, there's a dedicated video tutorial there on error intervals. Alternatively, you could scan this QR code. But in this video, we're going to focus on the video solutions to the practice questions, so let's get started. So question number one. Question number one says, the mass of a letter is 58 grams to the nearest gram. Complete the error interval for the mass of the letter. So let's find the lower bound and the upper bound for the mass of the letter. So let's start off with the lower bound. So we know that the mass of the letter is 58 grams to the nearest gram. So that means that it's been rounded to the nearest gram. So it could have been 57.9 grams. It could have been 57.8 grams because these both would round to 58 grams to the nearest gram. It could even be anything as low as 57.5 grams because that would still round to 58 grams to the nearest gram. But it could be anything below that. For instance, if it was 57.48 grams, that would round down to 57 grams, not up to 58 grams. So it couldn't be that, but that would be the lower bound. So the lower bound is 57.5 grams. So that's the lower bound. Let's now find the upper bound. So for the upper bound, let's consider the values that would round down to 58 grams. So it could be 58.1 gram. That would round to 58 grams. It could be 58.33 grams because that would round down to 58 grams. So it could even be 58.499 grams because that would round down to 58 grams to the nearest gram. So that means that the upper bound would be 58.5 grams because obviously it couldn't be 58.5 grams because that would round to 59 grams to the nearest gram, but it's anything up to that. So our upper bound would be 58.5 grams. So our lower bound is 57.5 grams and our upper bound is 58.5 grams. So now we know our lower bound and our upper bound, let's write that as an error interval. So the mass of the letter is going to be anything that is bigger than or equal to 57.5 grams, but less than 58.5 grams. And that's it, that's our error interval. Okay, let's have a look at our next question. Okay, let's have a look at question number two. So question number two says the length of a mobile phone is 142 millimeters to the nearest millimeter. Complete the error interval for the length of the mobile phone. So the length of the mobile phone has been rounded to 142 millimeters to the nearest millimeter. So let's find the lower bound and the upper bound, and that means then we can write our error interval. That shows the possible lengths of the phone. Now in terms of the lower bound, the length of the mobile phone is 142 millimeters to the nearest millimeter. So the lowest bound would be 141.5 millimeters. Now in terms of the upper bound would be, the upper boundary would be 142.5 millimeters. And then if we were to write that as an error interval, the length of the mobile phone would be anything that is bigger than or equal to 141.5 millimeters, but less than 142.5 millimeters. And that's it, so that's our error interval. It's saying that the length of the phone is anything that's bigger than 141.5 millimeters, but less than 142.5 millimeters. Okay, let's have a look at our next question, question number three. Okay, let's have a look at question number three. So question number three said the distance between two towns is 300 miles to the nearest 100 miles. Complete the error interval for the distance. So let's look at this. The distance between the towns is 300 miles to the nearest 100 miles. So in terms of the lower bound, well, the lowest number that would round up to 300 to the nearest 100 would be 250. So the lower bound would be 250 miles. And in terms of our upper bound, well, let's consider the numbers above 300 that would round down to 300 to the nearest 100. That would be anything up to, but not including 350. So the upper boundary would be 350 miles. So that means our error interval would be the distance between the towns is anything that is bigger than or equal to 250 miles, but less than 350 miles. And that's it. So that's our error interval. Okay, let's look at question number four. So question number four says Frank rounds a number y, so he's got this number y and he rounds it to the nearest 10 and his result is 80. Write down the error interval for y. So let's consider the lower bound to begin with. So he's rounding this number to the nearest 10 and the lowest possible number that whenever we round it to the nearest 10 to give 80 would be 75. So the lower bound would be 75 because 75 rounded to the nearest 10 would be 80, but anything below 75 would round to numbers lower than 80. And then in terms of the upper bound, let's consider the numbers in the 80s that would round down to 80 to the nearest 10. That'll be anything up to, but not including 85. So that'll be our upper boundary, 85. So let's now write that as an error interval. Now this time we haven't got our inequality written for us, we're going to have to write it ourselves. So his number y would be anything that is bigger than or equal to the lower bound, so that'll be 75, but less than the upper bound, which is 85. So the value for y that he could choose could be anything that is bigger than or equal to 75, but less than 85. So it could have been 77, could have been 80, could have been 84.99, and so on. So that's the error interval for the number that Frank rounded, y. That's it. Okay, let's have a look at our next question. So the next question says, Freya rounds a number y to 1 decimal place. So Freya's got a number y, and she rounds it to 1 decimal place, and her answer is 6.4. Write the error interval for y. So let's consider the lower bound to begin with, the lower bound. So that's the numbers that would round up to 6.4 when we round it to 1 decimal place. So that would be, the lower bound would be 6.35, because 6.35 would be the lowest possible number that when we round it to 1 decimal place would be 6.4. And now let's consider our upper bound. Well, let's consider the numbers that are bigger than 6.4. So that'll be anything that is up to, but not including 6.45. Because obviously 6.45 would round to 6.5, but anything up to that number would round to 6.4 to 1 decimal place. So now let's write our error interval. Y, the number that Freya rounds, would be anything that is bigger than or equal to 6.35, but less than 6.45. And that's it. So that's our error interval for Y. Okay, let's have a look at question number 6. So question number 6 says, a number p is rounded to 2 decimal places to give 10.68. Use inequalities to write down an error interval for p. So we want to write down the error interval for p, and it's been rounded to 2 decimal places. So let's consider the lower bound to begin with. So it's going to be the lowest possible number that would round to 10.68 to 2 decimal places, and that would be 10.675, because 10.675 would be the lowest possible number that would round up to 10.68 to 2 decimal places. Now, in terms of our upper bound, let's consider the numbers above 10.68 that would round down to 10.68 to 2 decimal places. Well, the upper boundary would be 10.685, because anything up to, but not including that number, would round to 10.68 to 2 decimal places. So now let's write our error interval. P is going to be any number that is bigger than or equal to 10.675, but it's going to be less than, up to, but not including 10.685. And that's it. Okay, let's have a look at question number 7. So question number 7 says, Elliot weighs 71.8 kilograms, and this mass, m, is to the nearest 100 grams. So this is his weight correct to the nearest 100 grams. And we're to write an error interval for m, so his mass. So in this, there's 2 different approaches which we can do this question. And one is to work in kilograms, or the other one is actually to change this into grams. I'm actually going to change it into grams and do that approach first, and then I'll do the other approach, keeping it in kilograms. So first of all, if I was to change this into grams, well, there's 1,000 grams in a kilogram. So if we multiply this by 1,000, we would have 71,800 grams. So that's his mass in grams, and the mass is to the nearest 100 grams. So let's write down the lower bound, and let's write down the upper bound. So in terms of the lower bound, let's consider numbers that would round up to 71,800 to the nearest 100. So the lowest possible number would be 71,750. That's the lowest possible mass that would round up to 71,800 grams to the nearest 100 grams. And in terms of the upper bound, let's consider numbers above 71,800. So if we consider the numbers that would round down to 71,800, the upper boundary would be 71,850. So all the masses up to, but not including that mass, would round down to be 71,800 grams to the nearest 100 grams. So we've got our lower bound and we've got our upper bound. Now we can write that as an inequality. So our error interval will be his mass, m, is greater than or equal to 71,750 grams, but less than 71,850 grams. So the error interval would be his mass is greater than or equal to 71,750 grams, but less than 71,850 grams. Now, because in the question his mass was given in kilograms, let's change both of these back into kilograms. So let's divide both of them by 1,000. So that'd be 71.75 kilograms. It's less than or equal to his mass, which is less than 71.85 kilograms. And that's it. So our error interval would be his mass is bigger than or equal to 71.75 kilograms, but less than 71.85 kilograms. And that's it. So that's one approach. Another way we could have done this question would have been, well, the mass was given to the nearest 100 grams. Now that in this case, because we're dealing with kilograms, that is to 1 decimal place. So really what this is saying is that his mass correct to 1 decimal place is 71.8. So it means the lower bound would have been 71.75 and the upper bound would be 71.85. And that's it. So the lower bound would have been 71.75, the upper bound would be 71.85, and then we could have written that as an inequality. So we could have used either approach. Okay, let's have a look at our next question. So the next question says, the length of each side of a rhombus is 5 centimeters to the nearest centimeter. Write down an error interval for the length of each side of the rhombus. So let's call that L, the length of each side. So L, the length of each side, is going to be greater than or equal to the lower bound, but less than the upper bound. Now in terms of the upper bound and lower bound, it's to the nearest centimeter. So the lower bound would have been 4.5 centimeters, because that's the lowest number that would round up to be 5 centimeters to the nearest centimeter. And in terms of the upper bound, that would be anything up to, but not including 5.5 centimeters. And that's it. So our error interval for the length of each side of the rhombus would be the length of each side is greater than or equal to 4.5 centimeters, but less than 5.5 centimeters. And that's it. Okay, let's have a look at part B. So part B says write down an error interval for the perimeter of the rhombus. So we want the error interval for the perimeter of the rhombus. So the perimeter is the distance around the outside of a rhombus. And remember, a rhombus is a quadrilateral where all four sides are the same length. So in terms of the lower bound for the perimeter, let's call the perimeter P. So the lower bound for the perimeter would be if we had the smallest possible length for each side. And if we look at the error interval for the length of the sides, that would be 4.5. So we'd have 4.5, 4.5, 4.5, and 4.5 centimeters for the length of each of them. And if we add up 4.5s, that would be 18 centimeters. So the lowest possible perimeter of the rhombus would be 18 centimeters. Now let's consider the upper bound, the largest possible perimeter of the rhombus. So the length of each side can be up to, but not including 5.5 centimeters. So what we're going to do is we're going to use the upper bound for the length of each side. So let's use the upper bound for the length of each side. And so I've now drawn the rhombus, but I've used the side length being the upper bound for the length of each side, being 5.5 centimeters. And if we do 4 5.5, so 4 times 5.5, that's equal to 22 centimeters. That means the upper bound for the perimeter would be 22 centimeters. It means the perimeter of the rhombus can be up to, but not including 22 centimeters. So let's write that down. The perimeter of the rhombus would be anything that is bigger than or equal to 18 centimeters, but less than 22 centimeters. And that's it. Okay, let's look at question number 9. So question number 9 says the length of each side of a regular heptagon, so a regular means all sides are the same length, heptagon, it's a 7-sided polygon, is 2.8 centimeters to 1 decimal place. Write down the error interval for the perimeter P. So we want to find the perimeter of this regular heptagon. So let's consider the lower bound and the upper bound for the length of each side. So for each side, the lower bound would be equal to, that's 2.8 centimeters to 1 decimal place. That means the lower bound, the lowest possible number that would round to 2.8 centimeters to 1 decimal place would be 2.75 centimeters. So that would be the lower bound for the length of each side. And the upper bound, well, the length of each side would be up to, but not including 2.85 centimeters. So that's the upper bound. So we've got the lower bound and we've got the upper bound. Now we've been asked to write the error interval for the perimeter of the regular heptagon. So here we've got a regular heptagon and we want to write the error interval for the perimeter of this regular heptagon. So let's find the lower bound for the perimeter of the regular heptagon and find the upper bound for the perimeter of the regular heptagon. So let's consider the lower bound to begin with. So if we were to consider the lower bound, the length of each side would be 2.75 centimeters. So it would be 2.75 centimeters, 2.75 centimeters, 2.75 centimeters, all the way around the regular heptagon. So if we just do 2.75 multiplied by 7, that'll give us the lower bound for the perimeter of the regular heptagon. So 2.75 multiplied by 7 is equal to 19.25 centimeters. So that would be the lowest possible perimeter of the regular heptagon. Now let's consider the upper bound. So let's consider the upper bound for the length of each side. Well, that was 2.85 centimeters. The length of each side can go up to, but not including 2.85 centimeters. And there's 7 sides. So if we do 2.85 multiplied by 7, that will be equal to 19.95 centimeters. That means the perimeter of the regular heptagon can be up to, but not including 19.95 centimeters. So let's write that down as an error interval. The perimeter is bigger than or equal to 19.25 centimeters, but less than 19.95 centimeters. And that's it. Okay, let's look at question number 10. So question number 10 says the length of a rectangle is 20 centimeters. So here's a rectangle and its length is 20 centimeters and its width is 6 centimeters, and both of those measurements are given to the nearest centimeter. So they're to the nearest centimeter. That means for the length, the lower bound would be equal to 19.5 centimeters. The upper bound would be 20.5 centimeters. So that's for the length of the rectangle. So the lower bound would be 19.5 centimeters and the upper bound would be 20.5 centimeters. In terms of the width of the rectangle, the lower bound for the width would be 5.5 centimeters and the upper bound would be equal to 6.5 centimeters. So they're the lower bounds and the upper bounds for the length and the width of the rectangle. Now we want to find the error interval for the area of the rectangle. So we want to find the area of the rectangle. Now to find the area of the rectangle, we'll multiply the length and the width together. And if we want the lowest possible area for the rectangle, we would multiply the lower bound by the lower bound. And if we want to find the upper bound for the area of the rectangle, we'd multiply the upper bound by the upper bound. So let's do that. So let's do the lower bounds. So 19.5 multiplied by 5.5 is equal to 107.25 centimeters squared. So that's the lower bound for the area of the rectangle. Now let's find the upper bound for the area of the rectangle. That'll be 20.5 multiplied by 6.5, and that's equal to 133.25 centimeters squared. So we've got the lowest possible area for the rectangle and we've got the upper bound for the area of the rectangle. Now let's write that as an error interval. So the area is bigger than or equal to 107.25 centimeters squared, and the area would be less than 133.25 centimeters squared. And that's it. Okay, let's look at question number 11. Okay, let's have a look at question number 11. So question number 11 says a band writes 2 songs, and the first song is 3 minutes long to the nearest minute, and the second song is 5 minutes long to the nearest minute. And we've been asked to show that the total length for the 2 songs could be 8 minutes and 58 seconds. Now, if we have a look at this time, this is bigger than the 2 times added together, but because we're told that to the nearest minutes, it doesn't actually mean the first song is 3 minutes long and the second song is 5 minutes long. It means that it's 3 minutes to the nearest minute. So it means the lower bound would be equal to 2.5 minutes, and it means the upper bound would be 3.5 minutes. So that means the song could be up to, but not including, 3.5 minutes long. And in terms of the second song, well, we're told that's 5 minutes to the nearest minute. So that means the lower bound would be 4.5 minutes, and the upper bound would be 5.5 minutes. So that means that the first song could be as short as 2.5 minutes long, but up to, but not including, 3.5 minutes long. And likewise for the second song, it could be as short as 4.5 minutes, and the length of it could be up to, but not including, 5.5 minutes. Now in this question, we've been asked to show the total length for the 2 songs could be 8 minutes and 58 seconds. Now if we add the 2 upper bounds together, that would tell us what the length of the 2 songs could be up to. It would tell us the upper bound for the length of the 2 songs. So if we do 3.5 minutes plus 5.5 minutes, that'll be equal to 9. So that means that the total length of the 2 songs could be up to, but not including, 9 minutes long. Now we've been asked to show that the total length of the songs could be 8 minutes and 58 seconds. Well, they can be. They could actually be 8 minutes and 59 seconds. They could be 8 minutes and 59.7 seconds, and so on. So let's write that down. And that's it. So I've just written down the upper bound for the total length of the 2 songs is 9 minutes, which is greater than 8 minutes and 58 seconds. Okay, let's have a look at our next question, question number 12. So question number 12 says x is rounded to 3 significant figures, and the answer is 12.7. Write down the error interval for x. So this time we've been told that the number's been rounded to 3 significant figures. So it's been rounded to 3 significant figures, and we've got 12.7. So let's consider the lower bound and let's consider the upper bound. So in terms of the lower bound, what's the lowest possible number that whenever we round it to 3 significant figures would be 12.7? Well, that would be 12.65, because 12.65 rounded to 3 significant figures would be 12.7. And then in terms of numbers above 12.7, which would round down to 12.7 to 3 significant figures, the upper bound would be 12.75, anything up to, but not including, 12.75. And that's it. So let's write down our error interval. X would be anything that is bigger than or equal to 12.65, but less than 12.75. And that's our error interval for x, the number that's rounded. Okay, let's look at our next question. Okay, let's have a look at question number 13. So question number 13 says a number y, so as a number y, is 9,200 when rounded to 3 significant figures. Write down the error interval. So we've got 9,200 and it's been rounded to 3 significant figures. So that actually means this 0 is significant. So let's consider the numbers below 9,200 and consider which ones would round to be 9,200 when we round it to 3 significant figures. So it could be 9,199 when we round that to 3 significant figures, it'll be 9,200. It could be 9,198 when we round that to 3 significant figures, it'll be 9,200. And it could be anything as low as 9,195, because whenever we round that to 3 significant figures, we would round the 9 up, so it'd be 9,200. And just to show you, it couldn't be 9,194, because if we look at the 4th significant figure, that's a 4, so that means that we won't round up the 3rd significant figure, so this rounded to 3 significant figures would be 9,190. So it couldn't be this, but it could be this, and this would be the lower bound. So the lower bound would be 9,195, and that's going to be less than or equal to y. And then in terms of our upper bound, let's consider the numbers above 9,200 and see which ones would round to 9,200 to 3 significant figures. So it could be 9,201. If we round that to 3 significant figures, it'd be 9,200. It could be 9,204. If we round that to 3 significant figures, again it would be 9,200. It could even be 9,204.989, because if we round this to 3 significant figures, and we look at the 4th significant figure, which is a 4, and that rounds down. So again, rounded to 3 significant figures, that would be 9,200. And it could be anything up to, but not including 9,205. That would be the upper bound. So that means that y, the value for y, would be anything that is bigger than or equal to 9,195, but less than 9,205. And that's it. That's our error interval. Okay, let's look at question number 14. So question number 14 is a bit different than the ones we've looked at so far. Let's have a look and see why. The length of the line L was given as 2.6 centimeters truncated to one decimal place. So it's been truncated, not rounded. Complete the error interval for L. So truncated is where whenever we have a number with decimal places, we just ignore the decimal places after a certain decimal place. So we've truncated this to one decimal place. That means we've written 2.6 and we've just ignored what comes after that 6. So it could have been, for instance, 2.64 centimeters, but we're just ignoring this 4. So we're just writing down 2.6. It could have been 2.68721 centimeters. And again, we're just ignoring anything after that first decimal place. So we just write 2.6. Even if we had 2.6999 centimeters, if we truncated that to one decimal place, it would be 2.6. We would just ignore what comes after that 6. So that means the lower bound, it could be anything as low as 2.6 centimeters, because it could have just been 2.6 centimeters, and when we truncate that to one decimal place, it would still be 2.6 centimeters. So it could be anything as low as 2.6 centimeters, and the upper bound would be 2.7 centimeters. It could be anything up to, but not including 2.7 centimeters. And that's it. So our error interval for the length of the line would be the length of the line is anything bigger than or equal to 2.6 centimeters, but less than 2.7 centimeters, and that's it. Okay, let's have a look at our next question. So question number 15, a number y is 0.04 when truncated to two decimal places. Complete the error interval for y. So obviously it could have been 0.04, and if we truncate that to two decimal places, it would still be 0.04. It could have been 0.041 when we truncate that to two decimal places, it would still be 0.04. It could be 0.0467 when we truncate that to two decimal places, it would still be 0.04. And it could even be anything as high as 0.04999. If we truncate that to two decimal places, again, it would be 0.04. So that means it could be anything up to, but not including 0.05. So that means that y is anything that is bigger than or equal to 0.04, but less than 0.05. And that's it. Okay, let's have a look at question number 16. So question number 16 says a number n is truncated to one decimal place, and the result is 39.1. And using inequalities to write down the error interval for n. So obviously it could have been 39.1. We could truncate that to one decimal place and it would still be 39.1. It could have been 39.18. When we truncate that to one decimal place, it would still be 39.1. It could even be 39.199, because if we truncate that to one decimal place, it would still be 39.1. And the upper boundary would be 39.2, because all the numbers up to 39.2 would have a 1 in that tenths column. So that'd be the upper boundary. So let's write down our error interval. The n, the number that's been truncated to one decimal place, could be bigger than or equal to 39.1, but it would be less than 39.2. And that's it. Okay, let's look at question number 17. Okay, let's have a look at question number 17. So question number 17 says Sahil solves an equation to find the value for x, and his answer for x is 8.25. His teachers realise that Sahil has written down the first 3 digits of x from his calculator display. So that means he's truncated his answer to 3 digits. He's just written down the first 3 digits and just ignored what comes after it. And part A says write down the error interval for x. So because he's written down the first 3 digits, well, it could have been 8.25, and that could have been what the teacher was looking at and just said he's written down the first 3 digits. But it could have been 8.251, and he's just looked at the first 3 digits. It could have been 8.25667, and he's just looked at he's just written down the first 3 digits. It could even have been 8.259, and he's just written down the first 3 digits. It's going to be anything up to, but not including 8.26. So that's the upper bound. So that means that to write down the error interval for x, it means that it would be x is going to be bigger than or equal to 8.25, that's the lower bound, and less than 8.26. So anything up to but not including 8.26. Okay, part B. Part B says explain why Sahil should not have truncated his answer. Well, whenever you're looking at your calculator, it's actually probably better to round your answer than it is to truncate it, because, for instance, if it was 8.259, it's much closer to 8.26 than it is to 8.25. So I think it's better to round than it is to truncate. So let's write that down. And I've just written down rounding would be a better option than truncating. For instance, his answer could have been very close to 8.26, such as 8.25999. And that's it. Okay, let's have a look at our next question. Okay, let's have a look at question number 18. So question number 18 says, when asked her age, Summer says that she rounds her age to the nearest year. And when asked her age, Kira says that she truncates her age to the nearest year. Who uses the most common approach? So actually, Kira uses the most common approach. I'm just going to write that down. Kira uses the most common approach because it's normal to truncate ages. So for instance, if Kira was 23 and it was her birthday, she would say she was 23. A month later, if you asked her age, she would say she was 23. halfway through the year, when she was 23 and a half, if you ask her her age, more likely than not, she would say that her age is still 23. Even a month before her birthday, if you asked her age, she would say she was 23. And then whenever it's her 24th birthday, then she would say she was 24. But the day before, she would still say she's 23. So we're truncating the age. We're ignoring the decimal bit after the decimal point. So she's not saying my age is 23.987 or whatever. She's just saying 23. Whereas Summer says that she rounds her age to the nearest year. Now, if Summer was 17 exactly and you asked her age, she would say she was 17. If she was 17 and a couple of months old and you asked her age, she would round that to the nearest year, so it would still be 17. But if it was 17 and a half exactly, so 17.5, and you asked Summer her age, she would say she was 18 because she's rounded up. And that's not normally what we do. We don't halfway through the year just round our age up to the next age. So whenever we're dealing with ages, we tend to truncate them. We don't go up to the next year until we've had our birthday, and so on. Okay, let's have a look at our next question, question number 19. Okay, let's look at question number 19. So question number 19 says the perimeter of a regular pentagon is 18 centimeters to the nearest centimeter. So that means the lower bound for the perimeter would be 17.5 centimeters and the upper bound would be 18.5 centimeters. So that's the lower bound for the perimeter of the pentagon and that's the upper bound for the perimeter of the pentagon. And we've been asked to use inequalities to write down the error interval for the side length x. So we want an error interval for the length of each side. Now it's regular, so that means that all sides are the same length, and it's a pentagon, which means it's got 5 sides. So if we divide the perimeter by 5, we can find the length of each side of this regular pentagon. So if we consider the lower bound, let's take our 17.5 and let's divide that by 5 and see what we get. And that would be equal to 3.5 centimeters. So that means the lower bound for the length of each side would be 3.5 centimeters. Now let's consider the upper bound for the length of each side. So let's consider the upper bound for the perimeter of the regular pentagon. That was 18.5. And if we divide that by 5, because there's 5 sides, that would tell us the upper bound for the length of each side of the regular pentagon. And whenever we divide that, we get 3.7 centimeters. So that means that each side is going to be bigger than or equal to 3.5 centimeters, but less than 3.7 centimeters. So let's write that down. X is going to be bigger than or equal to 3.5 centimeters, but less than 3.7 centimeters. And that's it. Okay, let's look at question number 20. So question number 20 says a woman runs 400 meters to the nearest 10 meters. So that means the lower bound for the distance she ran would be 395 meters and the upper bound, the boundary, would be 405 meters. So anything up to but not including 405 meters. And it takes her 80 seconds to the nearest 10 seconds. So that means the lower bound for the amount of time taken would be 75 seconds and the upper bound, it would have taken her up to but not including 85 seconds. So that's the lower bound and upper bound for the distance ran, and that's the upper bound and the lower bound for the time taken. And we've been asked to work out the error interval for her speed s. So what we need to do is for her speed, find the lowest possible speed, the lower bound for the speed, and we need to find the upper bound for the speed. Now in terms of the speed, let's work out the lower bound to begin with. So let's work out this for the speed. Remember, speed is equal to distance divided by time, so distance divided by time. We want to find the lower bound for the speed, so lower bound for speed. Now in terms of the lower bound for the speed, that's going to be doing the smallest distance in the greatest possible time. Because if you run the shortest possible distance, the 305 meters, in the longest possible time, that's going to give you the lowest result for the speed. So if we did the distance, 395 meters, and divide that by the time taken, and we're going to choose the biggest possible time taken because that'll give us the lowest speed. So we're going to divide by 85. That would be equal to 4.647 and so on meters per second. So that's the lower bound for the speed of the woman. So in terms of the upper bound for her speed, the upper bound is going to be found by doing the biggest distance in the shortest time. So if we do 405 meters divided by 75 seconds, that'll give us the upper bound for the speed. And whenever we do 405 divided by 75, that's equal to 5.4 meters per second. So we've got the lowest possible speed and the greatest possible speed, or the lower bound, the upper bound for the speeds. So that means we can write the error interval. The speed is going to be bigger than 4.647 and so on meters per second, and it's going to be less than 5.4 meters per second, and that's it. Okay, let's have a look at question number 21. So question number 21 says the number y is 100 when rounded to one significant figure. Circle the correct error interval for y. So let's consider the numbers below 100 that whenever we rounded to one significant figure would be 100. So if we had 99, if we round that to one significant figure, that would be, well, because it's a 9, it rounds up, so it would be 100 to one significant figure. If we had 98, if we round that to one significant figure, again, that would be 100. If we had 96, if we round that to one significant figure, because it's a 6, we round up, so it would be 100. If we had 95, if we round that to one significant figure, well, because it's a 5, we round up, so again, that would be 100. But if we had 94, if we round that to one significant figure, so that would work, that would work, that would work, that would work. If we had 94, if we round that to one significant figure, the answer would be 90. So that means the lower bound for y, the lower bound would be 95. So straight away I can rule out that option, I could rule out that option, I can rule out that option, I can rule out that option. So I'm left with these two options here, here and here. Now what we need to do is consider the upper bound. So we need to consider the numbers above 100, that whenever we round it to one significant figure would give us 100. So let's consider 101. If we round 101 to one significant figure, well, that would round to 100. Let's go a bit bigger. Let's try 120. If we had 120 and we round that to one significant figure, that would be, because this is 2, we don't round up, so it would be again 100. If we had 149 and we rounded that to one significant figure, that would be 100. But if we had 150 and we round that to one significant figure, because the second significant figure is a 5, we round up, so that would round to 200. If we had 150 rounded to one significant figure, that would be 200. But anything up to, but not including 150, would work. If you had a 149, if you round that to one significant figure, that would be 100. So that means that the lower bound would be 95, but the upper bound would be equal to 150. So that means that for y, it could be any number that is bigger than or equal to 95, but anything that's up to, but not including 150. So the error interval for y would be this one. And that's it. Okay, let's have a look at our next question. Okay, let's look at question number 22. So question number 22 says the area of a circle is 50 centimeters squared to one significant figure. That means the lower bound for the area would be 45 centimeters squared, because obviously when you round that to one significant figure, that would be 50. So that's going to be the lower bound. And in terms of the upper bound would be 55 centimeters squared, because anything up to, but not including 55 centimeters squared, would round to be 50 centimeters squared to one significant figure. So that means the lower bound for the area of the circle is 45 centimeters squared, and the upper bound is 55 centimeters squared. And we've been asked to find the error interval for the circumference of the circle. So what we're going to do is, well, we know the area of a circle, area is equal to pi r squared. So what we're going to do is we're going to use each of these to find the lowest possible value for the radius and the greatest possible value for the radius, so the lower bound for the radius and the upper bound for the radius. Once we know the lower bound for the radius and the upper bound for the radius, then we can work out the circumference of the circle, and we can work out the lower bound for the circumference of the circle and the upper bound for the circumference of the circle, and then we can write that as an error interval. So let's start off with the lower bound. So we're going to have 45 is equal to pi r squared, then divide both sides by pi, so divide by pi and divide by pi would give us the radius squared is equal to 14.3239 and so on. And we want to find the radius, so let's square root that. So that means if we use the lower bound for the area of the circle, the radius would be 3.784698 and so on. Now we want to find the circumference of the circle. So remember, circumference equals pi times diameter. So if we double this radius, we'll get the diameter, and then we just multiply by pi, and that will give us the lower bound for the circumference of the circle. So let's do that. So whenever we take the radius and we multiply by 2 to get the diameter, that gives us the diameter 7.56939 and so on. And when we times that by pi, we get the circumference, so the lower bound for the circumference, and that would be 23.77996 and so on centimeters. So that's the lowest possible circumference of the circle. That would be if the area was 45 centimeters squared. Now let's consider the upper bound. So for the upper bound, we'd have the area is 55 is equal to pi r squared. We want to divide both sides by pi to find out then what the radius squared would be. And whenever we do 55 divided by pi, that gives us the 17.50704 and so on. And then whenever we square root that, we'll find what the radius is. So the square root of that is equal to 4.18414 and so on centimeters. So that would be the upper bound for the radius of the circle. Now we're going to multiply that by 2 to get the diameter. And whenever we multiply the radius by 2, we get the diameter, which is 8.36828 and so on centimeters. And the circumference would be pi times diameter. So we're going to multiply this by pi. So the circumference is pi times 8.368 and so on. And that's equal to 26.28973 and so on centimeters. So we've got the lower bound and the upper bound for the circumference of the circle. Now we can write that as an error interval. So let's do that. And that's it. So we find the circumference of the circle is bigger than or equal to 23.779 and so on centimeters, but less than 26.2897 and so on centimeters. And that's it. So these have been the video solutions to the error interval practice questions. I really hope you found this video useful. If you do need any extra help on error intervals, there's video 377 on Corbettmaths. If you found this video useful, please like it and please subscribe to the YouTube channel. Thanks so much. Cheers. Bye.